All right, so today we're moving into sort of a different part, a different block in the course, a different chapter, if you will. And we're going to start by discussing a little bit just why. So far we have been concerned a lot with the what I call the macroscopic description that we use for light and light transfer in a lot of astrophysical applications. If you remember, we also talk about these two other ones, you know, in the photon descriptions, and we have the electromagnetic wave description, which of course is the classical description of light waves. So in this, we worked a lot with our basic transfer equation, which I'm now writing in this generic form here. Just this is the path length S, right? Now, the thing is that the interaction coefficients here, we sort of left them unknown. Yeah, we analyzed this in quite some great detail, but we never really discussed, so how do we obtain this? We formulated this in terms of the optical depth, which is just the extinction times the integral of the extinction over a path length, right? But we never, okay, how do we obtain them? So we learned also that we can write this in different forms, right? So this is per unit length, but particularly when we did the random walk of photons and we associated this with the optical depth, we learned how we could write this also as a cross-section times number density or an occupation number of the interacting particles, all right? So of course now, in order to obtain this and to actually calculate the optical depth, for example, we need to know how to get them. So this we typically call the occupation number, or something like that. It could also be like the number density of free electrons. If we're concerned with one of our main applications, it could be the occupation numbers of some state in an atom. For example, we concern ourselves a lot with the hydrogen atom. Now, this is the cross-section, as we saw, yeah, for the interaction. And that is what we will concern ourselves with in this chapter. And specifically, we will do so for scattering processes. Okay? And for the type of scattering processes that we will deal with here, which is essentially Thomson and Rayleigh scattering, but we will also make the transition and discuss line scattering already here. We can use the electromagnetic wave description, the classical description of light. So the first thing occurs, okay, but why do we step away from this at all? Well, if you consider this, this was based on array description. Remember, we had the macroscopic, we had the radiative transfer equation. Light traveled along a bunch of rays here, and you had some interactions over some material. And then we analyzed the properties there, right? But now, of course, we're interested in not just putting these interaction coefficients up, but we're interested in obtaining them. So say that we have some cross-section material here, right? Now, then we have to consider, okay, if we now have an incoming electromagnetic wave of light, if we take that with some sort of wavelength lambda, and then we interact with the particles here, say we have some electron that we interact with, then this lambda is the typical wavelength of light, right? But that now we have to consider what scale does this interaction occur on? Well, this interaction then actually occurs on, say, the atomic scale. And we don't know yet, we will learn that during the course, what type of scale to associate with that, but we know that it's very small. And typically a radius there might be something about an angstrom, right? Now, if we look at the wavelength of light, say optical light, we know that that's on the order of, say, 5,000 angstrom or something like that. Yeah? So we see here that for that part, lambda is typically much, much greater than the interaction length. And then this ray concept here, where we have to consider essentially bundles of light, an ensemble, if you will, a light ray, breaks down. We cannot use it. It's the same argument as when we can and when we cannot use geometric optics. So we have to go into that in order to describe this interaction. Now, we can still use for our calculations later on the macroscopic theory, that is radiative transfer theory, provided that we calculate these interaction coefficients using different concepts. So, okay, in this view that we will take here now, you can consider then, right, you have an incoming light wave here with some sort of frequency, lambda, or wavelength lambda, frequency. Say that we're interacting here, and this chapter we'll consider scattering processes, right? We interact with some electron, which then might scatter this light, okay, schematically. Now, in this way, we can define the cross-section here as the direction coefficient here between the incoming flux of the electromagnetic wave and the emitting power of the, in this case, the oscillating electron. Okay? So often in this part we use a different notation. Here I adhere to our previous one, which actually I didn't, because then I should say that this should be the emitting luminosity, right? Energy per unit second. But in this case, this is often denoted by S, the incoming flux, and sigma nu equals then to the emitting power, okay? And we can make that association for the right-hand side is that, okay, what is power is then, in that sense, just the surface integral of a flux over the A, okay? But it's easy for us to make the connection with our previous notation here, because we knew, for example, if we say that this is the luminosity, power is energy per unit second, that was our luminosity. That's also the surface integral over our flux, the A. And if we take this now, to just give you the simple example of a star, right? That's a radial star, then we got that this is just a radial flux, and then just the surface area, which was the solid angle 4 pi, and then radius squared. Okay, so that was just the simple way to make this connection. So what we see here is that we need some sort of expression to get the flux in this description and the power then by the emitting particle. With that, we can get to the cross sections, which we then can use in our theory that we have for radiative transfer that we use. All right, now, so the task now is to get these, of course. And for that, since we're in the classical description of light here, we will start with Maxwell's equations, which are, I'm just going to first write them down, then just okay, so what do we have here? Well, this describes the electromagnetic, the electric field and the magnetic field. These are Maxwell's four equations, where this, of course, is his unifying equation. Now, a few notes. Rho here is now the charge density. And J is the current density. So J, and that is the charge density times V, where this is then the velocity, okay? In this case. Furthermore, I will continue here to use CDS units, okay? Gaussian units, sometimes called here. It has some convenient properties, specifically one that the absolute values of the electric and the magnetic fields in these units are the same. Again, there are translations for you between the SI system and this CDS system, depending on what textbook you might follow in order to get to the Maxwell's equations, which is a topic for another course, so we won't do that here. You might find them in SI or in CDS units. So one has to work with the translations. Now, the first exercise for you here, of course, is to, and this is in the lecture notes, is in the course book, is to assume that you have no charge density, that is, you have a vacuum solution, okay? Now, if you set that to 0 here, then you can show from these equations, it involves some vector identity, that Maxwell's equation here satisfy a wave equation for, say, E, but also for B, of course, with speed of light c. Right? That's the whole thing. Now, we will now go ahead and we will consider a few other things. So, for that, we have to introduce the Lorentz force as well. Now, the Lorentz force is just Q E plus B divided by C cross B, okay? And we're going to write this in this chapter as Q E. This means that we consider only where V over C is much, much smaller than 1 or the non-relativistic limit here, okay? Furthermore, typically here we're going to say that, okay, we're going to, for simplicity, work where the charge density equals to Q, and we're going to set it typically to the electron. That's just a single charge, right? Which, of course, could also be positive, but for simplicity of notation, etc., we're going to take it to be the electron. Now, all right. So we're going to consider the work done here when we have a charge, okay? So the work in this case is just V dot product with the force, which in this case is just V QE or JE, where J then is our current density. Okay? And then we're going to see what this is by using Maxwell's fourth equation there. So we're going to just plug this over and see what comes out. We have C divided by 4 pi, right? And then we're going to have cross B, okay, dot product E minus 1 over C d E dt dot product E, okay? And then again, today I'm going to leave out some algebra for you. This is another algebraic exercise where you will have to use, I will actually state this vector identity for you because it's, yeah. If I wrote it down, you can use the generic vector identity as follows. Okay? So you use that, and you have to use one of the plus one more of Maxwell's equations, okay? Here we used Maxwell 4, right? This one. I'm going to have to use one more in this little algebraic exercise to show that this can be written as plus d dt e squared divided by 8 squared plus b squared divided by 8 pi equals to negative the divergence of Okay, we're gonna take off the right hand side of the board already now so that we don't okay. E cross B. All right. So here we have Poynting's theorem. Actually, it's Poynting's theorem in differential form. Yeah? If you were to take the integral over a volume and then use the divergence theorem, or Gauss's theorem, from your calculus course, then you could also get it into integral form, okay? But what I wanted to show here and why I wanted to put it in this form is that we can see that this has the same form of a conservation law as we have discussed before in our previous chapter, okay? So in that sense, we can actually use this to define some properties of the electric and magnetic fields. So in this case, we have the work term here, and then we have plus d dt of an energy density equals to negative the divergence of a flux. So this is how we can identify the energy density of the electromagnetic field as U equals to E squared 8 pi plus B squared 8 pi, which in our CDS units is just E squared divided by 4 pi, because the absolute values of these were the same, which was a convenient property. Now, here I have to make a note, and this isn't unfortunate, but it's also custom in the field, that remember when we used the macroscopic description for astronomy, then our big E was our radiation energy density, right? Now, here, big E is the electromagnetic field, and little u is our energy density. This confusion in notation is, of course, very unfortunate, but it is, I should say, always clear from the context, and it's just, yes, how it is standardly being used. So I also follow that here. Now, in this case, we can identify the flux, which I now will, again, write as S, because it's normally, well, it's denoted here instead of F. So that's C times 4 pi, and then it's just E cross B. And this is typically called then the Poynting vector, or the Poynting vector flux. Okay? All right. Well, we can look at the sanity check here, right? Using what we have learned about flux. So first, if we look at the absolute value here, we see that it is directly C divided by 4 pi, right? And then E squared, which in this case is just C times the energy density, yeah? And that sort of, in this case, makes sense. It is the speed times the energy density. And also, if we were to put it down, say, remember we discussed what a flux really is to some extent previously. We can have some sort of plate, and then we have the wave of radiation going in this direction now. This is some area A, and it would have some width C dt, okay? Then we know that our flux in this, okay, we have just parallel and we have defined the area, so it's just in this direction. Then the magnitude would just be the E dt 1 over A, where this is the total energy per unit time, so energy per unit time per unit area. That's our flux, right? But of course, we can write this, the E as our energy density, right, times the volume. And the volume here, the energy density we had, if we just plug that in, that was just E squared divided by 4 pi, right? Yeah. And the V in this case would just be A C dt. So we can see by just identifying that this divided by dt then, t's cancels, a's cancel, and the only thing we're left with is indeed E squared 4 pi c, or U times c. So they sort of say make sense in that respect. All right. I wanted to make one more connection here now to our previous sections, and that is that, okay, let's now consider a plane wave, which is how these electromagnetic waves are traveling as plane waves in the sense of its intensity, which was our specific intensity, which was our previous definition. And that was, we had it as a function of theta and phi, remember? Now, a plane wave is only going in one direction, so it will be some I0, and then it will be a delta function around some angle 0 and some angle phi 0, okay? And this is now the Dirac delta function that, again, you used in the previous part where we discussed the specific intensity and worked with it to do some exercises. And indeed, you actually did this exercise. Because now, if you consider what E is, in this description, now E is the radiation energy density. So now is where we have to take a breath and see that when we work with this description, this is the radiation energy density. When we work with this description, it's the electric field. That was just 1 over c, right? I, and then the omega. But in this case, since it's a delta function, this just comes out as I0. So this is then just I0 divided by c, okay? So if we put this now together with this, we see that the energy density times c is just I0 in this case. So can we make then contact with the other one? Yes, we can. However, since we have waves here, electromagnetic waves, that oscillate very fast with the speed of light, c, in fact, we have to take an average over one cycle in order to make this connection, okay? So if you think about such an electromagnetic wave, in this case, a plane wave, it will be something like E0, and then a cosine function, and then you have your kx minus omega t, right? So if you take that now and you average this over one cycle, because that goes with the speed of light c, so it just oscillates too fast in order to be put here. So we have to average it out, you know, because we don't know which phase we're coming in with. Then this is the same as the energy density then. The mean energy density of this would be the mean of E squared, right? Divided by 4 pi. So what is the mean of E squared? Well, this one is just the amplitude, so that's just the constant E0 here. And then it is just the mean of cosine of squared, right? So mean of E squared would be E0 squared, then the integral of theta 0 to 2 pi, in this case cosine squared d theta divided by 2 pi. Now this one you should be very familiar with, you know. We just use our standard transformation to write this in the form of 1 minus mu squared d mu, okay? That's just mu cosine theta, and then you transform it, okay? So you can just do this and get the answer oh my God. Now I did the wrong transformation here. My apologies. I was thinking ahead of another. This is of course not, because mu is cosine of theta. You can do this integral yourself. It will come out as 1/2 when you divide it off by 2 pi. So this is just z squared divided by 2, which means that the energy density here, the average value, is E0 squared divided by 8 pi. So if we now make contact then with our description for the intensity, we identify this with the average value of little u, which is E0 divided by 0, 8 pi. We can see directly that I0 divided by C is E0 squared divided by 8 pi. And there you have sort of a connection there. Now, you could do, and you have done, the same exercise for, instead of the energy density, the flux, and then identify this with the Poynting vector flux. And you would get the same sort of relation, that is, that if you considered such a situation and you calculated then the magnitude of the flux here, it would be indeed the energy density, now I use that, times the speed of light c, which then is the same as the average there is u times c, okay, where we would have this. So again, we can see that in the streaming limit, we get this relation between the energy density and the speed and the flux magnitude. All right, so now we have that. The second thing that we wanted was the power, right? So the power then, as we already said, is the integral of the flux, yeah, surface area, okay? So in our case, if we go back to our little sketch of the incoming wave, the electron, and it was scattering around, and we will have the electron oscillating, then this will be then, it will spread out spherically again, such that this is then the integral over omega. The flux here will be the Poynting vector flux, which we had as E squared C divided by 4 pi, and then we have an R squared there and the omega. So the task then is to find, okay, we need now for the electron, which is oscillating or accelerating, an expression for the electric field in order to get out what the power radiated by it is. Okay? And that's what we will do now after a break.